Hello, this is Arun Srinivasa. I am here to help you to learn engineering mechanics and its use in structural design. This is a quick recap of free body diagrams. I am not teaching you how to do free body diagrams from scratch. I'm just giving you a quick recap. So I'm expecting that you probably already know free body diagrams. You just need to get a brush up and some philosophical ideas about what should or should not be there in a free body diagram. Okay, so that's the purpose. Okay, so what is the purpose of a free body diagram? I want to introduce you to what is called the causality rule, which says that in our system, the way in which we think about mechanics is to say that force is the cause and motion is the effect. Okay, so why does this matter? It matters to free body diagrams. The idea is that every component is designed to perform a particular function, whether you look at gears, cams, chain drives, pulleys, pinions, etc. In order to carry out its function, the component will have to interact with its surroundings and withstand the external stimuli. Example of external causes include forces or couples, heat, light, and so on. But we are focused mainly on forces and couples. Structural design means designing a component to withstand forces and couples, which are the causes, okay? And to move in a prescribed way, including no motion. And these are the effects. Notice that the causes are to be able to withstand forces and couples. The effect is no motion. I will repeat this many, many times because I want you to get into this idea, okay? A free body diagram is a way to isolate the body that we want to analyze, like shown in the picture, and list all its external causes alone, not effects, only causes. That's why it only has forces on it, because those are the causes, okay? The equations of equilibrium together with the response relations like Hooke's law, etc., will then allow us to find the effects. So we use the free body diagram to figure out the causes. Then we use Newton's laws and other things to figure out the effects. That is how it works. Okay. Listing the causes is a key step as an engineer, and it cannot be automated. You have to do it. Every point in the body has either a known external force, including zero, or a known prescribed motion, including no motion. So this is called the duality rule. Okay. So remember, we had the causality rule. Now we are talking about the duality rule. Okay, they're linked, but the idea is that they're connected in some way. So in order to draw a proper free body diagram, the body in question must be completely separated, from the surroundings. So there's the box, and then only external causes must be listed. No internal forces between parts of the body. Only external causes must be listed. External loads must be listed at every point on the body. There are no exceptions. They can be known or unknown, but show them you must. In places where the effect is known but not the cause, we have to replace them with unknown causes. So here, I know the effect. That is no motion along the x direction. Okay, I have to replace it with an unknown cause. Here, there is no motion along the x and y directions. So I have to replace that with unknown causes. So there it is. So this is an unknown cause. Notice that its value is unknown. This is a known cause. This is the person standing on it. I don't know the effect, but I know that the cause is known. That's the weight of the man. Then weight of the ladder is another known cause. That's also listed. And finally, at this point, I have two unknown causes. Can you see that? So in places where the causes are unknown, I am assuming that you know the effects. And in the places, in the rest of the spaces, where the effects are unknown, I know the causes. And you're wondering, what about these pieces where I've not said anything? That's where the rule comes. If I don't say anything, I'm saying that the cause is zero. That is, there's no external force there. Okay, so I have prescribed every point in this body the cause for every point in this body. If I don't say anything, it's zero. That's all it means. Okay. Now let's talk about what does external load mean. From an engineering mechanics perspective, external loads are the only causes. Internal loads and deformations are effects. In this class, we will consider only two types of external loads. Actually, three. I'm being a little bit casual about it, so we will formalize it very carefully. These first type of external load are called contact forces that either push, pull, or drag the body due to its connection with the external world. So that's push. It's also called compressive force or pressure. That is pull, and it's called tensile force. And then there is drag, which is sliding or shear force. Okay, so this is contact force. The second one is contact couples that twist or bend the body due to its touch. This is somewhat rare, but nevertheless, there are common examples that I've showed you. One is like opening a jar, you're applying a contact couple, and or when you're trying to turn a nut, you're applying a contact couple. So that's the setup. Gravitational load, only very rarely. We don't usually show that, and that's it. There is nothing else. There are no other causes. Okay, now we come to the very critical item, which is called the independence principle, the constraint rule. And that says action-reaction principle does not apply to individual free body diagrams. Free bodies show only causes, not effects. So you need to replace the cause, the effect, known effect at connectors with unknown causes. So what the heck do we mean? So if you look at this connection, the simple beam, you can see that this connector here is at the wall, and its effect is it doesn't allow the bar to move at all. So I have to replace it with causes. So now what I want you to do is draw me a free body diagram of this piece. It's extremely simple, but please humor me and draw it. So what I want you to do is pause the video, draw it, and then look at how I am doing it. So then you can talk about it. Okay. So did you pause it? Did you draw the free body diagram? Please remember, you cannot build muscles by watching an exercise video. So watching me do it will not help you. Okay, so first I'm going to start out with the bar. I'm going to draw the free body diagram of the bar, and you can see the external force here. You probably drew this. You probably argued there has got to be a reaction force here because of this external force. And then you probably said that the external force has torque or moment, and you've drawn two moments, right, to counteract these things. If you thought about it this way, I'm not worried about whether a free body diagram is right or wrong, but this is an incorrect thought process. If you think this way, you will never be successful with complicated free body diagrams, and it will always look very puzzling. The reason is you're conflating equations of equilibrium with free body diagrams. Keep them separate. What do I mean? Here's what I would do. Here is this force again. So this part is the same as you. Now, I'm just going to draw three forces, which are constraint forces, since the wall joint prevents all translation. Can you see how I'm using the effect, which is prevention of translation, and replacing it with unknown causes, which is constraint forces? Same way, I'm going to draw three constraint moments, since the wall joint prevents all rotation. So the effect, which is the rotation, which I know, is replaced with unknown cause, which is the constraint moments. Notice that I've drawn three forces and three moments. And you're wondering, hey, wait a minute, what about these forces? Aren't they zero? Well, we don't care about them. We don't care about the values at all. We only care about the fact that they exist, that they're possible to be there. In a free body diagram, constraint loads depend upon the joints, not upon the applied loads in some other place. We will connect them up when we do equilibrium equations. So we'll wait for Newton. What's the hurry? So the main point is that you should draw free body one joint at a time without ever caring about the other forces. What I mean by that is, if you look at this picture, and if I want to draw a free body diagram of the man, I only care about this joint. I don't at all care about who is applying, what is happening here, nothing. Okay. Forces in a free body diagram are based on interaction and contact with external objects and not upon reactions to applied forces. This is a common mistake, so be careful about it. The word reaction force is a dangerous misnomer. The correct name is constraint load, not reaction load. Okay, we are going to use constraint load. Unfortunately, textbooks use reaction forces, and that's a problem. So now we come to this question. How do we then identify those effects and replace them with causes? And again, I'm going to emphasize this. External objects can cause motion, and then they are called motive forces, or they can prevent motion, then they are called constraint forces. Most textbooks refer to them as reaction forces. I want you to understand their purpose is to prevent motion. Right? We are going to call them constraint forces to prevent confusion with action-reaction principle. The effect of preventing motion will be obvious. That is what joints and connectors are there for. So to identify the effects, we look at each joint, find out what motion it prevents, and replace it with a corresponding unknown preventative load. And you've seen these things. That is what these kinds of diagrams represent. I'm sure you have seen that in your statics and dynamics class, where people drew these diagrams. So they tell you, for example, a pin or hinge joint allows free rotation, but prevents translation. So we have two preventative effects, causes, Fx and Fy, whose values are unknown. Same way with roller joints, which prevent y direction movement. So you got an unknown y direction cause. Rocker joint, same way. A link actually prevents motion that separates the 2 points of the link. So there is an unknown directional force, which is a cause. A fixed joint prevents both translation and rotation. So there are three. There's corresponding things on the side of 3 dimensions. I've put up, sorry for the bad picture, but I'm sure you have found a much better picture in your notebooks, in your textbooks. So I'm just trying to connect this up. Okay, so what kind of joints are there in a human body? This is just to tell you that the joints are not just something that we build, it's also there naturally. So look at how many different joints. So if you look at a neck joint, you will see that it allows you to freely rotate your neck. And that's what is called a prismatic joint, a rotational joint. You can see that at your elbow is able to move up and down. This is a good chance. Try it out yourself. And that way you'll get some circulation going also. So you can just try it out yourself. Then your wrist actually is able to move in 2 different directions. And that's called a saddle joint, or it's called a Hookean joint. But that's the kind of joint which is there at your wrist. Then you have a ball and socket joint at your hips. Then there is a kind of planar joint at your floor, and there is all these interesting joint which is called a condyloid joint. It's really a very fascinating and complicated joint. Okay, so these are the joints that you find in the human body. So now we come to the main challenge. How do you draw a proper free body diagram? So let's say I want to draw a free body diagram of this kind of gripper. So first, figure out the body you want to isolate. Let me make it very specific and say I want to draw the lower handle of this gripper. Then draw a full and complete outline. In 2D, it should be a closed loop that surrounds the body of interest. In 3D, it should be a closed surface. Can you see how I drew a closed loop? If you skip this step, you will pay for it. So don't skip it. It's very simple, but don't skip it. Locate and label the points where things are connected and where forces like gravity are acting. In reality, only the location of these points matter. The body itself does not matter. So Point number 1, I have a 100 Newton force. Point number 2 is a pin joint where I connected the two links together. And point number 3 is where the grip, whatever the object I'm gripping, is preventing these things from closing. Okay, there's contact there. Okay, now I'm going to draw this thing separately, and I'm going to draw my axis. You can put your axis anywhere you like. Those are my 3 points. Now, I'm going to draw the known forces, and then at each connection, corresponding unknown constraint load. So at point number 1, I have the 100 Newton force. At point number 2, it's a pin joint. That may be a pin joint. Where it is right now, I could consider it as a pin joint. If it is sliding somewhere else, then it would be a different kind of joint. You'll have to pay attention to what kind of joint it is. So I got 2 forces at this pin joint. And then I have a normal force at the contact point with the whatever I'm gripping, the gripping object, maybe a pipe or something like that. Please notice that it only has causes. Some of the causes are known, some of the causes are not known. So let's check and make sure we're drawing the correct free body diagram. Here is our free body diagram. How do I check it? First, did I draw the axis? Yes, check. Did I draw a closed and complete outline for the body we want to isolate? Yes, check. Did you mark the points where external loads act and CG if needed? CG is center of gravity. Yes, check. For each load, you should be able to fill in the blanks here. That says the load is here because some external body is pushing, pulling, dragging, bending, or twisting in this direction at this point. Notice it doesn't care at all about what else is happening, just at this one point. So let's see. Why is there a force F1y? Because my hand is pushing upwards at this point. What about F2x and F2y? The top handle is pushing or pulling upwards and sideways at that point. Why is there a force F3n? The bar that I'm gripping is pushing perpendicular to the jaws at that point. It says jassy, but it should be jaws at that point. Okay. Notice I have an explanation for why each force is there. And the explanation has nothing to do with motion. It only has to do with constraint or applied external force. Okay. We can simplify the drawings also. I'll do a 3D example to show you what I mean. Here's a 3D, it's a gear system with forces on it. I'm going to draw a free body diagram of this. I want you to try and draw it. I will draw it and you will see how I simplified it. Okay, so pause it, draw it, and check. Did you pause it? I told you, if you want to learn, you have to try it out yourself. Okay, so now I'm going to draw. So that's the motive force. That's what drives the gear. That's the force that leaves the gear from the other one. It's a kind of constraint force. There are 2 other constraint forces also, so we will draw all of them. So first of all, I replace. I'm not going to draw the full circle of the gear. I told you the only thing that matters are points of contact. So I just drew straight lines that represent the radii of the gear. That's really, really simple, right? So I can draw what is called a skeleton diagram. That's more than enough. Now, let's start. Here's the axis. Okay, now let's start with the motive force. There it is. I resolved it into parallel and perpendicular because it's easy to do. The radial force is 11 sine 20 degrees. The tangential force is 11 cos 20 degrees. Okay, then at joint O, it's constrained, and I'm writing the constraint forces ROZ and ROY. You can also put ROX. I have not put it for this one because in the actual solution, it was not there. That's all. Okay. Similarly, at point B, FBR and FBT, and then finally at point C, I have constraint forces RCZ, RCY. Notice it's just straight line. I can simplify this further if I move these forces down. Be very careful when you do that. I'm going to do that, and I'm going to show you that this is the final version. If I don't have, if I even remove the gears. So now notice I have 2 torques. Can you see? Torques that are going in opposite directions. So what it is that the first torque is tangential force times radial distance. The second torque is also similar, FBT times RB. Those are the two torques. Okay, so this is an example of free body diagram. I'm sure you've drawn these kinds of things before, but I'm just showing you what is possible. So now I'm going to talk to you about what are things that you should not do. So first item, don't draw free body diagrams directly on a picture. Isolate it first. If you do this kind of free body diagram, nobody will understand which arrow is what. Okay, so this is totally confusing. Never draw a free body diagram like this. Don't do this. You won't know how to analyze it. Almost everyone in the engineering community will be completely confused. So always draw a free body diagram as a separate item. It should actually be free. Don't move forces around. Keep them at the point where they are. To show you what I mean, here's a person. Yeah, you can see their weight. It's roughly at the stomach. And then you can see the normal force that's from the ground, right? Person is happy, everything is fine. Now look at this one. Do you think it's the same? Physics may say, okay, these two figures are the same, but think about it for the person. It makes a huge difference whether their force is acting from the bottom or from their neck. You're with me? The second one is in a bad shape, right? So please remember, don't do like that. Even though technically the two bodies are the same in physics, but they mean entirely different things in the real world. And it actually matters. So you have to use physics plus common sense. So therefore, don't move forces around in a casual way. Think about it before you do. Don't fall for fake forces. Free body diagrams are not fair and balanced. You're with me. I want you to understand that. So free bodies don't have to be balanced. Forces don't have to be balanced in a free body diagram. Let's see an example. I got a car going around in a circle, moving at a constant speed around in a circle. So you might draw tire friction and say, okay, there's something pointing inwards. And then you might draw a centrifugal force. This is a fake force. This will not, we will not do that. Our free body diagram does not care about Newton. If the forces are unbalanced, Newton says the body will accelerate. That's all. Let's deal with the acceleration when we write the equations. Okay. The correct way to do that is just this tire friction. Of course, I have not shown all the forces. There is normal forces, there is weight and all this stuff. I have not drawn any of those, just to illustrate this one point. Okay, so this is not a complete free body diagram. So please remember, our paradigm is forces causes motion, motion cannot cause force. So please remember that, okay? So the 5 rules of free body diagram, let us summarize. We started out with the duality rule. Every point in the body has either a known external force, including zero external force, or known prescribed motion, including no motion. The causality rule says external forces are the cause and motion is the effect. The isolation rule says FBD need to be isolated. Don't draw FBDs directly on the picture. The constraint rule says FBD shows only causes, not effects. So you need to replace known effects at connectors with unknown causes. The independence rule says forces in free body diagrams are not related to each other and they can be unbalanced. Let Newton take care of that later. So don't include fake forces just for balance. We are done. Thank you very much.